This is the first video in a series about building the column still that I designed to distill azeotropic alcohol. This video is about the boiler. I'm not the fastest video maker, and to avoid frustration of anybody wanting to build the still waiting endlessly to produce the videos, I have drawn up a series of plans that are available online as PDFs, which I link below. There is an online community of home distillers, but you will not be joining it by building my still, which is designed to run slowly for weeks at a time, unattended. Unattended still operation is a taboo in that community. You will get no help from them, partly because they do not engage in this practice, but mainly because they have no experience of it. The still uses a packed column because it's inexpensive and has a high yield for its diameter. But as is characteristic of packed columns, it has the disadvantage of only working optimally over a narrow range of alcohol vapour flow rates. That means we have to control the boiler power precisely. We need to increase the power substantially from the beginning of a run to the end to keep the alcohol vapour flow rate constant while the steam flow rate increases. That means controlling power in the range 100 to 350 watts with a precision of better than 1%. The boiler heater's rated power will typically be several kilowatts. I use 2 kilowatts. Wiring a variable resistor or rheostat in series with the heater element to control its power would work, but it's not practical because of the amount of heat that would be dissipated in the rheostat. So an alternative solution is needed, and there are several options. A variable transformer, or variac, is a transformer with a secondary coil that's tapped by a wiper arm that's moved with a large knob. They are heavy and expensive, typically costing $200 for a 2 kilowatt one. They are, however, durable, reliable and efficient, and put low stress on the heater, leading to a long heater life, but they don't lend themselves well to automated control. If you have one available and are using manual control, it is a good option. Another option is to power the heater with direct current from a variable switch mode power supply. That works well, but for the voltages and currents required they are not widely available, and they are very expensive. Triac control is the most common method to vary the power of lamps, motors or heaters powered by alternating current. It works by turning the heater on or off at specific points during the AC waveform, as shown here. The top graph is the AC supply voltage. In the second graph, every time the AC waveform crosses zero, the heater is turned off. It's switched on again at a variable time point after this zero crossing. If the delay to switch on is short, most of the wave is sent to the heater, as in the second plot. If that delay is lengthened, the proportion of power sent to the heater falls, as in the third and fourth plots. It's a good, precise system and is comparatively inexpensive. You can get a 4 kilowatt triac controller for around $20, and it is a good option for manual control system. It puts a lot of inductive transients onto the power line, which could be a problem if you have other sensitive equipment close by, though those can be suppressed with capacitors. I originally built my still control system in the period of chip shortages, and there was no readily available means of automating triac control, so I used a different approach. That has changed, and these hats, short for hardware attached on top, for the Arduino or Raspberry Pi are now available. This is a programmable 2-channel triac control dimmer system that will operate up to 2.1 kilowatts per channel. Larger triacs can be piggybacked on if greater power is required. I haven't evaluated these, but the datasheet looks promising, and were I starting now, I'd examine one because they avoid the compromises necessary for my pulse width modulation system. Triac control does not readily lend itself to automation, and this is a complex microcontroller-based circuit costing around $30. Pulse width modulation works by turning the heater on at full power, then off in a regular cycle, so that the average power delivered is determined by the proportion of time for which it's on. I suggest using a small board computer like a Raspberry Pi. It can be done with a simpler system than that, but future development of the still involves computerized control, and starting with a small board computer will give you valuable familiarity with it and will avoid having to purchase more electronic equipment in the future. Any small board computer will do. I've used Raspberry Pi 0s, 3s and 4s. The zeros are cheap, but they only have one USB port, so you need a dongle to expand the USB port number and add an Ethernet connector if you're using a zero without Wi-Fi. The dongle adds costs and makes the zero's advantage marginal. Also, the 3s and 4s are faster. Overall, I'd say it's worth spending the extra cost to have a faster internet and avoid the dongle and failure-prone connections. You select one of the GPIO pins and program the Pi to switch it high to low with a software-controlled duty cycle. The Pi can't control a 2 kilowatt heater directly, and we do not want to use relays. Non-sealed relays produce sparks that can ignite alcohol vapor, so pose a fire risk. That can be avoided by using sealed relays, but another reason to avoid relays is that they tend to fail on. When switching mains voltages, each switch movement makes a spark, and the sparks slowly erode the coating on the contacts. They're good for around 50,000 cycles, which you use up pretty quickly in this application. When the coating is burned through, the sparks weld the contacts together, making it fail on, leading to a dangerous situation, particularly if the still is left unattended. Solid-state relays and MOSFETs make no sparks and fail off, so are acceptable solutions. Solid-state relays are used for switching AC, MOSFETs for DC. Both have internal heat dissipation and need a heatsink. You'll also need some form of thermal grease or conductive strip to go between the semiconductor and heatsink. Solid-state relays have an LED that is illuminated when they're on, which is quite convenient. They do not tolerate inductive loads, so get an immersion heater for the main supply voltage that you have available, as you cannot include a transformer or variac in the switched circuit. I set it up like this, with the solid-state relay mounted on top of the heatsink and the heatsink screwed to a board so that the relay's LED is visible. The circuit is quite simple. The solid-state relay has a DC side and an AC side. The DC side is the gating current. It has a negative and positive and can be gated by a voltage of between 2 and 20 volts. Using the GPI output voltage of 3.3 volts works fine. We connect the Pi ground to the negative of the DC side of the solid-state relay and our selected GPIO pin to the positive side. Then we connect the heater in series with the solid-state relay. When it's all set up, get to programming. Video is a poor medium to communicate that, as you really need to have things written down, so I cover that in the plans linked below. The pulse width modulation frequency is selected to be a compromise between two constraints. The first is that we need a continuous vapour output from the boiler. As we're constantly turning the heater on and off, there will be a variation in the output of the boiler that gets more pronounced the lower the frequency. Electric hot plates like this use the same pulse width modulation system to control power, but their frequency is much too slow for constant vapour flow, which is one reason why they're unsuitable for this application. The other being that they contain sparking switches. The minimum frequency that allows a steady vapour stream depends on the characteristics of the heater. I have found that a cycle time of 3 or 4 seconds is marginal. Less than that is okay with the immersion heaters I use. The other constraint on frequency is to do with the way solid-state relays operate with alternating current. They come in two forms, zero crossing and random switching. The zero crossing type are a lot cheaper, about $5 compared to $100, which is why I use them. They only switch when the AC voltage crosses zero. Mains voltage supplies are either 50 or 60 Hz. A 50 Hz supply crosses zero 100 times per second, and a 60 Hz 120. As we're not synchronizing the solid-state relay with the AC wave, we get delays between changing the GPIO pin and the solid-state relay switching. The delays are in effect variables between 0 and 10 milliseconds per switching for a 50 Hz supply, so 0 to 20 milliseconds per cycle. If we're controlling a 2 kilowatt heater, the maximum random variation in the 50 Hz case is 20 milliseconds per 2-second cycle, or a duty cycle variation of 1%, giving a potential error of up to 20 watts. Not great, as we're aiming for a precision of 1 watt. This error would fall proportionally if we reduced the frequency, but we can't do that, as I explained. It would also fall if we reduce the immersion heater rating. We're safe because over many cycles these variations average out and give only a slight random wobble to the steam output of the boiler, which I have found to be tolerable. A random switching solid-state relay would improve this problem, but I've not tried one as they're pretty pricey. Turning to the boiler, any design will do. I suggest it be between about 10 and 50 litres. Tuning the column is easier if the alcohol content of the vapour changes relatively slowly as the run progresses. The smaller the boiler, the faster it changes, and for this reason I wouldn't recommend going under about 10 litres. On the other hand, if it's more than 50 litres, it gets too heavy to easily handle when full. Aside from that, the design is unimportant, and I suggest using whatever is to hand. I used a 50-litre stainless steel milk churn from AliExpress like this. I added a 2 kilowatt immersion heater that again I got from AliExpress. If you use a lower power immersion heater, you'll get more precise control of the azeotropic distillation process, but I use the same heater for stripping runs and a lower power heater would make that slower. A good solution would be to have two heaters, a high power one and one of about 500 watts. Then use the high power one or both together for stripping and the low power one for azeotropic distillation. It is convenient to have a power plug and socket on the immersion heater circuit so that it can be unplugged and is not permanently connected to the still control board. We don't want any sparks, certainly not near ground level, and the immersion heater is going to be on continuously for several hours while it's heating the wash up to the boiling point before distillation commences. So you need to choose a plug and socket that is good quality with a high enough current and voltage rating. I have the control board at desk height above the floor and plug the boiler into that. You have to modify the lid to take the column. I'm using a 28mm diameter 1500mm long copper pipe for the column and use a brass 28mm tank connector to connect it to the boiler, which requires a 35mm hole cut with a hole saw. That's quite easy to do for these churns. You take the handle off the lid and use the small hole where the handle screws in as a pilot hole. You can connect the column to the tank connector using a compression fitting, but it's a little bit inconvenient as you want to be able to use the boiler as a stripping still with a Liebig condenser when it's not connected to the column. This needs an additional component, some kind of step-down connector from 28 to I use 15mm in order to fit a silicon rubber hose to convey the vapour to the top of the Liebig condenser. I explain how to make that kind of thing in a video on small copper components. A more convenient but somewhat more expensive alternative is to use tri-clamp connectors. They can be bought to fit the BSP threads of the tank connectors and have various hose connection options for your stripping still. If you're handy with a TIG welder, you can save cost and complication by just welding a 1.5 inch tri-clamp ferrule to the lid and soldering another to the column bottom. The boiler then needs to be insulated with any material to hand that can withstand moderate temperatures. In the next video I'll turn to the column extension and top, but these things are all explained in the plans.